everybody. So we're now on our next video on number theory, and today we're going to talk about the Euclidean algorithm. Okay, so we have talked about this in the previous video and this preliminaries of it, and now we're going to illustrate the theorem number 5. So we call this a theorem number 5 just for the sake of, naming it for now, because we'll be using it in the future, in the Euclidean algorithm proper, in the proof of it actually. So we're just going to give some illustrations for the theorem number 5. That is, we're going to give some applications of it, okay, including, or rather, in the application of it in the GCDs, in the greatest common divisor. So let's just have a recall what theorem 5 is. So it says that let this a and b be natural numbers, and r be the remainder rather. So when a is divided by b, then the greatest common divisor of a and b is equal to the greatest common divisor of b and r. That is, a and b, the GCD is equal to the GCD of b plus the remainder and the remainder. So to illustrate this theorem, we need to have some examples. So first example will be this. I don't know. Let's just put it here above. Okay, so we have a lot of space. So for this is the what states here is that we're going to illustrate theorem number 5 with a equals 120 and b equals 28. So for the solution of it, let's write it down. Solution. Now we first need to verify, or we may see that what is a GCD. We can see, notice, shall we have that? Notice the GCD of 120 and 28 is equal to 4. How do we get that? So if you want the step-by-step solution for it, so let's see, 120, 28. Let's get the prime factorization. So 120 is 2 times 60, 60 is 2 times 30, 30 is 2 times 15, 15 is 3 times 5. Okay, and then for the next one, we'll have the 28. So the common factors of 28 is 2 times 14, 14 is 2 times 7. So we have here as the prime factorizations of 120, 28. So it's clearly going to be seen here that we have the common factors 2 here and 2 over here, and there's nothing more common factors. So we can say that the GCD rather, the GCD, oops, the GCD of 120 and 28 is equal to 2 times 2 or 4. That's equal to 4. Okay, so that's our first example for the GCD of, just to verify that the GCD of 120 and 28 is indeed 4. Now, by using the division algorithm, recall the division algorithm. So by the division algorithm, by the division algorithm, we can see that this can be equal to 120 equals 4 times 28 plus 8. Okay, so 120 is equal to 4 times 28 plus 8. What happened here, sir? So this is our A, or shall we say this is our dividend? This is our A. This is our B here, the divisor. This is our Q, and this is our R, the remainder. So again, our A is this, our quotient is this, our divisor is this, and our remainder is this. Okay? So by the theorem number 5, it states there, so by theorem number 5, by theorem 5, we can see that the GCD of 120, 28 is just equal to the GCD of 28 and 8. Okay, and notice also the GCD, okay, the GCD, the GCD of 28 and 8 is also equal to 4. How can we check that? So let's say 28 and 8. 28 is again 2 times 14, 14 is 2 times 7. How about 8? 8 is 2 times 2 times 2. So indeed, we can see that the greatest common factor is a single 2 and the second 2. So we can say that the GCD indeed, the GCD of 28 and 8 is equal to 2 times 2, which is equal to 4. Okay, so indeed, this is correct. So therefore, we can say, okay, therefore, if we cannot get the GCD by the first method, so we can say that 120 GCD of 120 28 is equal to 4. Okay, so that's the end of our solution. There. So what we have shown is by theorem 5, we have we took or we got the GCD of A and the GCD of B using the theorem. Okay, so this is actually the part wherein if you want to get it directly, so we can. Okay, that's it. And by using the theorem, we can see it here. Okay, we can see it here. Okay, so next example will be evaluating this. Okay, so for the next example, let's have this number 2. Using theorem 5, so we will evaluate the GCD. Let's it cannot fit here. Evaluate the GCD of 2000, 2000, 2076 and 1776. So let's try to get the GCD of 2076 and 1776. Notice if we're going just if we're just going to get this directly, that cannot be. It's gonna be a tasky job, right? It's going to be very much tasky. So what we will do is using the theorem 5, we will try to evaluate that. So for our solution, okay, for our solution, apply the division algorithm. So we will apply the division algorithm, okay, with 2076, okay, which is the larger of the two numbers. So it should be emphasized that it is the larger of the two numbers as the dividend, as the dividend, and the other number, the smaller one, 1776, as the divisor. Okay, and then we can see by the division algorithm, the picture will be like this. 2076 is equal to 1. There's only 1776 from 2076. So 1 times 1776 plus 300. Okay, that's the difference. Okay, now what we're going to do is again reapply the division algorithm by theorem 5 using again theorem 5. So we will apply again. So apply again. Um, apply again the division algorithm with the our b to become the dividend. So 1776 as the dividend and 300 as the divisor. So what we will have is what we'll have is um 1776 is equal to how many 300s are there in 1776? So we can see that it's 5. It's only using 1500 because the next number is 1800. So 5 times 300, the remainder is 276. Now, actually, what we will do is to continue this procedure. Okay, setting now this one as our dividend and this one as our divisor. So we will continue using that method. So if you want to have a clearer view, okay, that is by the repeated application of theorem 5. So if you want to have clearer view, so let's put it here. See, it can fit. Um, okay, to put it all here. Let's have it. The first one is 2076 2076 equals 1 times 1776 plus 300. Okay, the next thing is what we're going to do is to put this as your dividend and put this as your divisor. Okay, so what will happen, we know this in the next step is 1776 equals 5 times, what's it, 300 plus 276. That's our next step. Now, we're going to continue this process, putting this 300 in dividend this time, putting this remainder as the divisor. So if we continue that, we'll have 300 equals how many 276 and 300? That's only 1 times 276. What's the remainder? Just subtract it plus 24. And we'll continue this process. 276 will be now the dividend, 24 will be the divisor, and what we'll have is 276 equals how many 24s are there in 276? Clearly more than 10, so let's just have 11. 8 times 24. The remainder is 12. And for the last step, for the last thing, okay, here, we'll continue the same process. 24 becomes the dividend, 12 becomes the divisor. So what will be it? So it's gonna be like this, 24, okay, plus equals, okay, 24 equals, um, how many 12s are there in 24? So clearly there are two. Okay, there are two. 2 times 12, and I think the remainder is 0. Okay, so we stop there. Okay, we stop with the last um, non-zero. This is the last. Okay, just take note. This is the last non-zero remainder. Okay, okay, last non-zero remainder. Okay, so this is your last non-zero remainder, 12. So by repeated application of theorem 3.11, what do we have? Okay, what do we have by repeated application? Let's write that. By repeated application of theorem 5 rather, theorem 5, we have, or we can say that the GCD of 2076 and 1776 is equal to the GCD of 1776 and 300, which is equal to the GCD of 300 and 276, which is still equal to the GCD of 276 and 24, which is equal to the GCD. I don't know where to put it anymore. This is the corner one. Which is equal to the GCD. Shall we put it here? Equal to the GCD of 24 and 12. And what is the GCD of 24 and 12? Clearly, it is 12 itself. Okay, just 12 itself. So let's kind of erase this. Okay, so therefore we can say since the GCD is of 24 and 12 is 12, so therefore we can say then by our answer, okay, um, thus we can say that the last non-zero remainder in this procedure is the GCD, that is 12. Furthermore, we can say now, okay, we can state from this, okay, that the GCD, I think we'll put therefore the GCD of 2076 and 1776 is equal to 12. Okay, and this is our answer for the second number, 12. Okay, so with this, we have illustrated theorem number 5, and yeah, in the next video, we're going to actually define now in in or justify the algorithm, although it's now obvious in this procedure how the algorithm works. Okay, so yeah, let's do that in the next video. Okay, I hope you would like and subscribe, and thank you so much for watching. Okay, see you.